So this is part 165. It's line 18A, 3z3d NSTX reduced collisionality plasma confinement density control W7-X 5G Wow Seti. And there's the Wow Seti radio signal, the alien radio signal. And there's the answer to the equation. It says March 8, 2012. Today's date is March 14th, 7:41 p.m. So my thoughts from March the 8th. I'm looking at the NSTX tests. Tokamaks, ITER, plasma heating and collisionality factor is in this data. How can we solve their problem for them? Quote, an important goal of NSTX upgrade is to assess reduced collisionality and to study how this influences plasma confinement. So I'm going to take a look at this picture here. It says confined plasma, vessel wall, core plasma, antenna, scrape off plasma. So this is a schematic of the 2D NSTX polodial cross-section used in the simulations. And I got that from burningplasma.org. So I'm going to pull out the keywords for presentation. Data to read for research purposes is plasma confinement by magnetic fields. Found on www.fusion-eur.org. Principle. Left to itself, a plasma, like a gas, will occupy all the geometrical space available because of the collisions between the particles. Magnetic fields can confine a plasma because the ions and electrons of which it consists will follow a helical path around the magnetic field lines. If a vessel containing plasma is placed in a rectilinear magnetic field, the particles of plasma cannot reach the side walls, but they will strike the ends of the vessel to prevent the particles from coming into contact with the material walls. In this way, two types of magnetic configuration have been studied. Linear configurations, in which the intensity of the magnetic field is increased at the ends of the container so that the particles are reflected by the magnetic mirror before they can come into contact with any material. Unfortunately, particle collision effects render the system liable to high particle losses at the mirror points, and such systems are no longer being considered as potential reactors. Toroidal configurations, in which the risk of losses is removed by curving the magnetic lines around to form a closed loop. Theoretical study of particle trajectories show that if the particles are to be confined, the toroidal field must have superimposed upon it a field component perpendicular to it, a polodial field. The force lines of the total field thus become spiral, helical, paths along and around which the plasma particles are guided. There are several types of toroidal confinement systems, each with its own method of producing helical magnetic field lines. The main types are Tokamaks, Stellarators, and reverse field pinch devices. Now, as you know, in the previous videos, we've looked at Tokamaks and Stellarators as well. They keep coming up in different forms and shapes, and there's a lot of new material, new devices that are being created, and there's a lot of new test results that are coming up for them. And in this portion here, there are about 4 videos from the one video. I split it into 4 sections because of all the data that came up. So you'll want to watch the next 1, 2, 3, 4, 5 videos to make sure you get everything. Okay? So, and I am looking at definitions and stuff because I didn't know what all this stuff meant. So, in the tokamak, the toroidal field is created by a series of coils evenly spaced around the torus, and the polodial field is created by a strong electric current flowing through the plasma. In a stellarator, the helical lines of force are produced by a series of coils which may themselves be helical in shape. No current is induced in the plasma. And in a reversed field pinch, RFP, device, the toroidal and polodial components of the field are created as in a tokamak, except that the current flowing through the plasma is much stronger than in a tokamak with the same toroidal field. The magnetic fields are set up on a time scale such that they undergo a spontaneous internal reorganization, and the direction of the toroidal field within the plasma is reversed. Then we have plasma heating and toroidal configurations. In tokamaks and RFP devices, the current flowing through the plasma and creating the polodial component of the magnetic field also serves to heat the plasma by the Joule effect until a temperature of about 10 million degrees is reached. Now, Joule comes up in the 6EQUJ5, the actual alien signal itself. J stands for Joule, so this will be a keyword here. We have plasma heating and toroidal configuration. So obviously, whatever they're working on here with the Joule, this is important for the UFO engine, okay? So by the Joule effect, until a temperature of about 10 million degrees is reached. Beyond that point, the resistivity of the plasma is too low for there to be significant dissipation, so additional heating systems have been developed to bring the plasma to temperatures necessary for fusion. So they're still trying to get plasma to create fusion, okay? In the case of stellarators, these heating systems have to supply all the energy needed, since in this magnetic configuration, no current flows within the plasma. Okay, so that's what it looks like. Here's another pretty little picture for you to look at. This is a rear view of a natural beam injector for heating the plasma in the jet Tokamak. So they're using a beam to heat the plasma. Now, isn't that funny? I didn't know anything about this stuff, okay? And in some of my formulas, I talk about using a laser beam to heat up the plasma. So I thought this was kind of cool to find out that they actually do that. So I'm on the right track. Okay? So neutral beam injection heating, an ion beam created and accelerated outside the confinement device, is neutralized before entering the vacuum vessel. The neutral atoms are ionized in the plasma and confined by the magnetic field. Collisions redistribute the energy and the temperature of the plasma increases. Then we have another device here. It's called a heating and current generating antenna for the FTU Tokamak. That's quite the antenna. It's huge. That's bigger than huge. I didn't even know that was an antenna. That's funny. Okay, so it's, you see the words there. Okay. Radio frequency heating. Plasma can absorb the energy of electromagnetic waves at its own characteristic frequencies, in particular the cyclotronic frequencies of the ions and electrons. Antennae fed by powerful wave generators line a part of the reactor wall. The frequency selected determines the type of particle which will be heated and the region where the wave will be absorbed, and thus where heating will occur. And then we adiabatic compression of the plasma. This method involves moving the plasma from a region affected by a weak magnetic field towards a region where there is a strong magnetic field. This is achieved by gradually increasing the vertical component of the magnetic field. As this involves a pulsed mode of operation, there again we are talking about pulsed laser beams, which is another thing that comes up in the Wow Seti signal, which makes considerable technical demands on the machine. It is little used. Only TFTR Princeton, USA has used it in recent times. And this is based from Fusion Expo 2003, again from fusion-aero.org. So I'm going to Google density control on particles. So we got I have a PDF file. It comes up called Nuclear Fusion Volume 45 from D. Sharma from 2005. It says three-dimensional Monte Carlo simulations of W7-X plasma transport, density control and particle balance of steady-state operations. There's the name of the different doctors that did it. And the abstract is, this paper presents self-consistent three-dimensional 3D plasma transport simulations in the boundary of Stellarator W7-X obtained with the Monte Carlo code EMC3-EIRENE for three typical island diverter configurations. The chosen 3D grid consists of relatively simple nested finite toroidal surfaces defined on a toroidal field period and covering the whole edge topology, which includes closed surfaces, islands, and erodic regions. Local grid refinements account for the required high resolution in the divider region. The distribution of plasma density and temperature in the diverter region, as well as the power deposition profiles on the diverter plates, are shown to strongly depend on the island geometry, i.e. on the position and size of the dominant island chain. Configurations with strike point positions closer to the gap of the diverter chamber generally favor the neutral compression in the diverter chamber and hence the pumping efficiency. The ratio of pumping to recycling fluxes is bound to be roughly independent of the separatex density and is thus a figure of merit for the quality of the configuration and of the diverter system in terms of density control. Lower limits for the achievable separatex density, which determines the particle exhaust capabilities in stationary conditions, are compared for the three W7-X configurations. And it looks like they studied transport properties, stellarators. There's all there. That's what they studied in this file here. All the things that they looked at. And that's at science.iup.org. Now, these are the names of all the videos that all the information is going to be in. And again, I divided up into different sections so that we can look at each one by one, okay? So line 18A, 3Z2B, 8B is, actually I'm not going to read this, I'm just going to let you look. There you go. It's just easier for me, okay? Because I'm losing my voice already, my throat's sore. These are all the topics that are going to be in the videos. They all came together. Oh, see, there's 5G. That means there's, when you see 5G, that means it's got something to do with the formula. So you have to pay attention to it. And we're going to talk some more about rotation. I found some more stuff about plasma rotation, all sorts of stuff. Okay? So that's it. And here's the tags for the video so you can see what all the topics are that we're going to be covering in these 4 videos. Actually, each video has its own set of tags, just so you know. Just look at them real quick. Okay, and we'll go on to the next video.